Ladies and gentlemen, you are all welcome to my YouTube channel. In today's video, we are going to look at the concept of isomerism in carbohydrate. If you could remember, ladies and gentlemen, from our previous lecture, we discussed about the different classification of carbohydrates. So in today's lecture, we are going to look at the concept of isomerism of carbohydrate, and briefly let's look at the classification of monosaccharide based on their number of carbons. Generally monosaccharides are sugars that can be described as, or let me just say in general, carbohydrates are generally classified or can be defined as polyhydroxyaldehyde or polyhydroxyketones, or any compound that produces such on hydrolysis. Like for example, now let's look at this compound here. This is glucose. So if you look at the glucose here, is a typical example of monosaccharide, and of course we see that from here there is a carbonyl carbon, and this carbonyl carbon is aldehydes. So that is why we said it is polyhydroxyaldehyde. So we call it polyhydroxyaldehyde because, of course, there are many OH group. And OH group is called hydroxy. So that is why it is called polyhydroxy, because there are so many OH groups. So that is why it is called polyhydroxy. And of course, there is an aldehyde functional group. That is why it is described as polyhydroxyaldehydes. And in addition, of course, the carbohydrate have two important functional groups, and these two main important functional groups is number one, aldehyde and ketone. And of course, in my previous lecture of carbohydrate, I seriously discussed this aldehyde and ketones. So, of course, carbohydrate monosaccharide is the simplest. Is the simplest monosaccharide. Sorry, is the simplest carbohydrate because it's of course described as monosaccharide because it can never be hydrolyzed to produce more other sugars. So it cannot be hydrolyzed. So that is why it is called simple sugar or monosaccharide. So the simplest monosaccharide among the monosaccharide, we have classified them based on the number of carbon. So the simplest carbohydrate that we have, of course, is 3 carbon. It's 3 carbon monosaccharide. So we have monosaccharide that have only 3 sugars. And examples of these sugars, or the name that we call these simple sugars that have, of course, 3 carbon is called trioses. The word tri means 2, 3. So trioses, it means that they are monosaccharides that contain only 3 carbon. They are monosaccharides that contain 3 carbon. And examples of these trioses that we have as carbohydrates, we have glyceraldehyde, we have dihydroxyacetone. So glyceraldehyde, of course, is aldose. The word aldose, it means that it's a 3 carbon sugar that have aldehyde functional group. That is why it's called aldose. And then we have dihydroxyacetone. So dihydroxyacetone, example of dihydroxyacetone, we have ketotriose. Of course, here is a mistake. So it's ketotriose. So ketotriose means they have ketone functional group. And of course, this is the typical example of the glyceraldehyde, and this is dihydroxyacetone. So this is the example of triose that have 3 carbon. And then we have tetroses. Tetroses are those sugars that have 4 carbon, and examples of the tetroses, we have triose, we have erythrose, and we have triose. So these are the examples of 2 tetroses. The erythrose have aldehyde functional group, while triose have, of course, ketone functional group. Then another example, we have pentose. That is those sugars that have carbon, that have 5 carbon. So they have 5 carbon, and examples of this sugar, we have arabinose. Arabinose is an example of sugars that contain 5 carbon. And then the next one is actually hexose, the one that have 6 carbon, and examples we have glucose. So this is a typical example of hexose, glucose. It has 6 carbon. And then the next thing is heptose. So heptose are those sugars that have 7 carbon, and examples we have pseudoheptulose, and then we have monoheptulose. So monoheptulose and stereoheptulose are the monosaccharides that have 7 carbon. So these are actually the typical examples or the classification of monosaccharide based on their number of carbon. So the next thing that we are going to look at, of course, is the structure of glucose. So let's look at the glucose more closely. So the carbons in the glucose molecules are linked by covalent bond. So all the carbon that are found in glucose, they are linked with one another using covalent bonds. So which on breaking yield energy to an organism. So these carbon bonds that are found in glucose, so when you break them in the living organisms or in living organisms, they generate energy. That is why we say carbohydrates is energy giving food, because they are actually rich in covalent bonding, which as a result of the breaking down of this covalent bond, it yields energy that actually sustain our life. So glucose molecules comprises of 12 hydrogen. So it has 12 hydrogen. So if you count this number of hydrogen, we are going to have 12 hydrogen. And then of course, 6 oxygen. So 6 oxygen, 12 hydrogen. And of course, these 12 hydrogen and 6 oxygen atoms are bound to the parent carbon chain. So this is actually a linear form of glucose. It is a linear because it is a straight line, and then we have a cyclic form. So this is a linear form of carbohydrate, and this is the cyclic form of carbohydrates. So then the next thing that we are going to look at, ladies and gentlemen, of course, is isomerism in carbohydrates. So ladies and gentlemen, what is isomerism? So when we say isomerism, it refers to the phenomenon where compounds have the same molecular formula, but different structural or spatial arrangement. So in this case, actually, we have, of course, compounds that if you see them, their molecular formula is the same. But in terms of the structure, they are different. And this difference can be as a result of this in terms of the structure or in terms of the spatial arrangement of the atom. So as we are continuing the lecture, we are going to see clearly how this isomer operate and how one compound differ from one another based on the structural arrangement or spatial arrangement. So isomers are compounds that have the same molecular formula but different structure. Like for example, you can have a compound, let's say, of course, let's say we have C. Okay, let me just give example. Let's say we have C. Okay, let me actually delete this so that you can have a clear understanding of what the isomerism means. So actually in isomerism, it's a situation where you have, let's say you have C4H10. So this is actually butane. This is butane. So butane have 4 carbon and 10 hydrogen. So but structurally, butane can be something like this. It can be C, 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 C. And here we have 3 hydrogen atoms. We have 3 hydrogen atoms here. Here is hydrogen. Here is also another hydrogen. Here is also another hydrogen. Here is also another hydrogen. And here, of course, we have 3 hydrogen atoms. The last carbon. Forget about it because this is not part of the structure. So this is actually N-butane. We can call it N-butane. So why is it N-butane? Because it is normal. It doesn't have any branch. So, but you can have, in addition, you can have the same butane appear like this. So you see, even from here, you can see clearly, here we have 3 hydrogen. Here we also have another 3 hydrogen. And here we have 1 hydrogen attached here. And then here we have also another 3 hydrogen. So you can see clearly here, they have the molecular formula in the same, but in terms of structure, they are different. So this is what we call isomerism. So when you have compound having the same molecular formula, but different structure, that phenomenon is described as isomerism. But the arrangement of the atoms can be in terms, or the difference can be in terms of the structural arrangement or spatial arrangement. So in carbohydrates, isomerism plays a significant role. It plays a critical role in determining their biological functions and properties. So very interesting, ladies and gentlemen, what we need to understand is that actually in isomerism, all these compounds, they are playing a vital role. And this role that they are playing is actually involved in so many activities. Like, for example, some carbohydrate, because of this isomerism, can do, let's say, glucose. Glucose, it is actually the primary source of monosaccharide that can easily be degraded and generate energy. But this fructose is also a monosaccharide. It has the same molecular formula with glucose, but because in terms of the arrangement, they are different. So as a result of that, they have different functions. They have different function. So this isomer plays important role in biological functions and also properties. So understanding isomerism is essential for understanding carbohydrate chemistry and its application in biochemistry and nutrition. So of course, if you are able to have a good understanding of the concept of isomerism, it will give you an idea of understanding the concept of carbohydrate chemistry. Number one, it is application in biochemistry and nutrition, because in nutrition, a compound that have the same molecular formula, but because of its structure, because of its isomerism, it will make that compound to be of nutritional important. But in another case, you can have a situation where the same compound, the same molecular formula, but due to the isomeric form, it can actually cause disease or problem in humans. So then now, the next thing that we are going to look at is types of isomerism. So ladies and gentlemen, of course, we have different types of isomerism. These different types of isomerism include, number one, we have what you call structural isomerism, and then we have stereoisomerism. So structural isomers, ladies and gentlemen, you should get this. Structural isomers is actually isomers that differ in the arrangement of atoms. So it's actually based on the arrangement of atoms. Maybe you have a carbon, you have, let's say, methyl group at carbon 2, but in the other case, you have methyl group at carbon 3. So it's the same formula, but you see that the arrangement of the atoms differ in position or differ in arrangement. And that is what you call structural isomerism. While stereoisomer is actually they are isomers that have the same connectivity, but differ in spatial arrangement. That is how they arrange, how the atoms are connected, or how the atoms are spatially arranged. So in terms of the different spatial arrangement of the atoms is where we have stereoisomers. So then for structural isomers, it's actually based on the arrangement of the atoms. So each type of isomerism have significant implications for behavior and reactivity of carbohydrate. So as we continue with the lecture, we are going to look at, we are going to see how these different isomers have serious implications on the behavior of carbohydrate as well as its reaction. So these are the two types of isomer, structural and stereoisomers. So in terms of the structural isomers, is divided into chain, positional, functional, metamerism, tautomerism, ring chain. And then we have stereoisomer where we have geometric and optical isomer. So ladies and gentlemen, I'm not going to explain the details of these types of carbohydrate because I have a complete video on isomerism. So I'm going to attach the video on the isomerism after this class. And ladies and gentlemen, don't forget, please, try to join the YouTube community and also subscribe to the community. So once you actually come to this YouTube channel, please subscribe to the channel and then turn on your notifications so that whenever we upload videos, you watch and then you also join the YouTube community. So then, of course, let's look at the structural arrangement. This is a structural isomerism. So structural isomerism includes different forms such as aldoses and ketoses, which differ in functional location. So let's look at the structural isomer. So you see, if you look at the ketones or aldoses, those sugars that have aldehyde functional group or ketone functional group, so the most important thing that we should understand, the only difference between them is just the functional group. And the functional group is just that in ketone or in aldoses, there is a free hydrogen that attached to the carbonyl carbon, while in ketosis, the carbonyl carbon is attached with two different alkyl groups. But in terms of the molecular formula, they are the same. The number of OH group, they are all the same. That is why if you check glucose and fructose, they have the same molecular formula. But in terms of the arrangement, you will see that they are different. So this is actually examples of structural isomer. So for example, glucose and aldose and fructose and ketose have the same molecular formula, but different structures. So that is what I want you to understand. They have the same molecular formula, but their structure are different. That is why one is called glucose and the other one is called aldoses. So structural isomers also encompasses chain isomerism, which involves the variation in carbon skeleton. So this is what I want us to understand. So we have, if you need more explanation on chain isomerism, please watch my video that I'm going to attach it in this lecture. So what about stereoisomer? So stereoisomer can further be divided because in stereoisomerism, we said that it is types of isomerism where the compounds have, of course, the same connectivity but different spatial arrangements. So let's actually look at, we have two types of stereoisomerism. We have geometric isomerism and we have optical isomerism. So what is actually geometric isomerism? So geometric isomer result from the arrangement of groups around a double bond. So let's look at, this is a double bond. This is a double bond. So there are isomers that have groups that are around the double bond. So let's look at it. These are the groups. We have one here, we have another one, we have another one, we have another one. So this is isomerism. So you see, these are the four groups that are around the double bond. But the most important thing, look at the R here, the R and R here, they are on the same plane. They are on the same orientation. So that is why it is called cis. But look at the R here, it's transverse. So you see, in terms of the arrangement, it's not the same. That is why it is called trans. So it means that they have transverse arrangement. So they are called transgeometric isomerism. We have cis geometric isomerism. Then so we see in the geometric isomerism, because of the restricted double bond, they don't rotate and they have arrangement of groups around the double bond. So they are restricted. They cannot move because of the presence of the double bond. And then in addition, the optical isomers are isomers that have a chiral molecules that exist as enantiomers. So when we say a chiral molecules, it means that for a chiral carbon, we have chiral carbon. Chiral carbon is called stereogenic carbon, is called asymmetric carbon. It's also called alpha carbon. So whenever you have a carbon with four different groups attached to it, that carbon is called chiral carbon. So now, where do we have chiral carbon here? This is our chiral carbon. This is our chiral carbon. Because if you look at it here, this one is actually a carbon but in skeletal form. So here is free hydrogen. Here is OH group. So therefore, they are not the same. Then here is CH2OH and here is CHO. So this group and this group also differ with one another. So that is why this carbon is considered as a stereogenic carbon, or can call it chiral carbon, because there is the carbon attached with four different groups. And then in the case of this one, they are the same. So what actually make this one and this one differ from one another? So you see, look at the orientation of OH group and look at it here. So you see the OH group here is actually at the right and the OH group here is actually at the left. So this one that is at the left is called L-glyceraldehydes. And this one that have OH group on the right side, it is called D-glyceraldehyde. So that is why in stereoisomerism or in optical isomerism, we have D isomer and L isomer. So most of the carbohydrates that are found in living organisms like we human, we found it in the form of D isomer. So D-glyceraldehydes is an example of the carbohydrate that have OH group at the right side. That is why it is called D-glyceraldehyde. And L-glyceraldehydes has OH group on the left. So that is why we have these isomers. So we have D optical isomers and then we have L optical isomer. So the presence of multiple chiral centers in carbohydrates can lead to a vast number of stereoisomers. So it is possible in carbohydrate to have a carbohydrate that have multiple chiral carbon. It's possible. So let's actually look at more closely on the concept of this optical isomerism in carbohydrates. So optical isomers, they are also known as enantiomers. So enantiomers is another name for optical isomers. So generally they have mirror image and they cannot superimpose. They have mirror image and they cannot superimpose. So chiral carbon are carbon, as I mentioned, that have multiple chiral centers. Sorry, chiral carbon are compounds that have different groups or 4 different groups attached to the carbon. It is also called stereogenic carbon. You can also call it asymmetric carbon. So carbohydrates often have multiple chiral centers, leading to enormous possible enantiomeric forms. So if you have a carbohydrate that have a vast or that have multiple number of chiral carbon, so it actually leads to enantiomic forms. So the specific arrangement of these chiral centers can greatly influence the biological activities of the carbohydrates. Like, for example, we in human, we don't even metabolize L-glucose. The enzymes that we have in our body is the enzymes that can catalyze D-glucose. So that is why these optical isomers play an important role in biological activities of the carbohydrate in living organisms. So you can see clearly, ladies and gentlemen, this is a chiral carbon. And of course, all the atoms are different. That is why here we are seeing 1, 2, 3, 4. So they are different. And of course, look at this 4 here. The 4 is at the right. That is why it is this. And the 4 here is at the left. That is why it is called, So now let's look at the examples of carbohydrate with multiple chiral centers. So you see, we have 1, 2, 3, 4. So the number of chiral carbon in glucose is 4. So if you want to know the possible number of enantiomic form of the glucose is to calculate the number of stereoisomers. So how do you calculate the number of stereoisomers? We use 2 power n, and n reflects the number of chiral carbon. So that is why here we have 2 power 4, and we have 16 stereoisomers. And that means we have a total of 16 enantiomic forms of glucose. So then the next thing is actually anomeric isomerism, which is also very, very important. So anomeric isomerism is a specific type of isomerism that occurs in cyclic forms of carbohydrates. So they occur in cyclic forms of carbohydrate. So it means that if you are looking for an anomeric isomerism, it's only found in a cyclic carbon. And it arises due to formation of a new chiral center at the anomeric carbon during the cyclization of monosaccharides. So this is actually, so we have two forms of this anomeric isomerism. We have alpha and beta, which differ in the orientation of hydroxyl group attached to the anomeric carbon. So this number one here, this carbon here is called anomeric carbon. This is the anomeric carbon. So you see, we have alpha D-glucose, alpha and beta. So what makes alpha and beta different is in the form of this one, the OH group is pointing downwards. It's pointing downward in the anomeric carbon, so it is pointing downwards. Then in the case of beta D-glucose, the OH group is pointing off at the anomeric carbon. So this is actually how to actually see the difference between alpha and beta. So for the alpha, the OH group at the anomeric carbon is pointing down, and for the beta, it is pointing up. So then the next one is Epimers. So Epimers are a subtype of stereoisomers or the stereomers that differ in configuration at only one specific chiral carbon. So they only differ at only one specific carbon, but all the arrangement, all the spatial arrangement are the same. So let's look at the mannose and the glucose. So you see, in the mannose, look at the mannose. So between mannose and D-glucose, what is actually the difference is only at the carbon to the orientation or the configuration of OH group here. So you see, it is only the configuration of OH group that make D mannose differ from D minus. Sorry, D mannose from D glucose is only at carbon 2 due to the spatial or due to the change in configuration of OH group. The OH group at carbon 1 in the case, also at carbon 2 in the case of mannose is at the left, while the OH group for D-glucose is at the right. And then the next thing is D-glucose and D-galactose. So for D-glucose and D-galactose, you see the only difference is also at carbon 4, the change in the orientation of OH group. So that is what I want us to understand. So in the case of Epimers, Epimers have only differ in configuration at only one specific chiral carbon. And of course, for instance, glucose and galactose are Epimers, different only at the carbon 4. So understanding epimerization is crucial in carbohydrate metabolism and enzymes reactions, because enzymes are very specific. So because of this difference in OH group around 1 carbon atoms, so enzymes that is specific to catalyze glucose cannot catalyze mannose because enzymes are specific. So what are the importance of isomerism in biological systems? So the isomeric forms of carbohydrate can have vastly different biological roles and activities. For example, only certain isomers of sugars can be utilized by specific enzymes in metabolic pathway. So this isomerism, they actually play a significant role in biological system. So one isomer cannot actually do the same work with another isomer. So for example, only certain isomers of sugars can be utilized by specific enzymes in metabolic pathways. And some isomers of sugars cannot be metabolized because we don't have enzymes that is specific for that isomer. So ladies and gentlemen, a simple term, what I want us to understand, the concept of isomerism is key and is very important. You have D-glucose and you have L-glucose, and you take L-glucose, the L-glucose cannot be metabolized. Although in some cases, if we have some intestinal bacteria, they may have such kind of enzymes and they will be utilized the glucose there. So that is why I wanted us to understand the concept of metabolism is the concept of isomerism is very, very important. So this specificity is vital for cellular processes, energy production, and overall metabolism, because enzymes are very specific. So some isomers are specific for cellular processes, energy production, and overall metabolism. So that is why we need to understand what types of sugar do we need in our body. So that is why understanding the concept of isomerism. Don't say glucose is glucose. So glucose are not the same. We can add alpha D glucose, we can have beta D glucose, we can have alpha L glucose, we can have beta L glucose. So they are not the same. So that is what I wanted us to understand. So what are the applications of carbohydrate isomerism? So isomerism in carbohydrate has significant application in food sciences, pharmaceuticals, and biotechnology. Because in food sciences, you need to understand what actually specific type of isomers that is important for our health. What are the specific types of isomers is important in drug development and drug prescription? What are the importance of carbohydrates that are required for some actually microorganisms to produce or to generate our biotechnology products? And in addition, the development of sweeteners, for example, often involved in manipulating isomeric forms to achieve desired flavors and functionalities. So in some cases, you can have some isomers. As a result of some small manipulation, you can change one isomer to another to give you an isomer of your desired interest, maybe flavors or functionalities. So it is very good. So understanding isomerism can also aid in drug design. So if you are able to understand isomerism, it can help you to design drugs. As specific isomers might exhibit different therapeutic effects. That is what I wanted us to understand. So ladies and gentlemen, this is just a brief introduction on the concept of isomerism and carbohydrates. So we need to understand this concept. So thank you very much. If this is the first time you are coming to my YouTube channel, subscribe and join the YouTube community. Thank you very much.